Hello, this video begins our introduction to quantum mechanics. We'll start by looking at the state of physics at the end of the 19th century, the beginning of the 20th century, where we begin to see some issues with experimental results that could not be explained by classical or Newtonian mechanics. Specifically, we're going to be looking at four significant failures of classical mechanics: black-body radiation, the photoelectric effect, both of which have to do with strange behavior of light that could not be explained with classical theory, wave-particle duality, where we ask what's the difference between the wave and a particle, and is it possible for something to behave as both? And then finally, line spectra, which are the kinds of things that you're looking at when you are doing a spectroscopic examination of a particular substance. And why do we see different substances with different spectral patterns? And specifically, why do different substances have different colors? This is something that couldn't be explained by classical mechanics. So since the first two of these particular failures have to do with light, we'll start out with basic description of light. This goes back to something you learned in general chemistry or even before that, but let's do a quick review of this. First of all, we know that light is oscillating electromagnetic radiation. This means it consists of two fields, an electric field oscillating up and down, as you see in this particular diagram, and a magnetic field oscillating, in this case, horizontally right to left. The issue is that the electric fields and the magnetic fields are perpendicular to each other as light propagates through space. All right, so we know it's oscillating and it behaves as a wave. But how do we know? What experimental evidence do we have that indicate that light does indeed behave as a wave? Well, let's first consider water. We know water travels in waves, propagates as waves, and so over here on the left side of the slide we see an example of a water waves emanating from two sources. These little red dots here represent the sources of these two waves spreading out circularly from each other. Now, the waves from these two sources will meet, and when they meet, we'll get interference between the waves, and here we have, I've drawn some red lines indicating where the waves, in fact, lead to very low amplitudes for those waves, where the waves meet, and tend to cancel each other out. This is something that's called an interference effect, and is something that is due to the behavior of waves when they meet and interfere with each other. So let's consider light and what happens when we pass light through here. We have double slits. So you can see these two little holes here. The light's propagating through these two slits, so we get a double slit pattern, just like we did with the water waves. And when the light waves strike this film here, we'll get this alternating pattern. For example, if the two waves emanating from the two slits come together here so that their crests match up, they'll add together in a way that leads to an even larger crest. This is something that's called constructive interference. And if we have a situation where we have a crest and a trough arriving at the film in the same spot, then these two will cancel each other out, leading to no displacement at all. This will be a dark spot in the pattern that appears on the film, and of course this corresponds to these quiet areas from the water waves. So this is something that is very specific two waves where you get constructive interference and destructive interference. In the case of light, the constructive interference leads to bright spots on the film, and destructive interference leads to dark spots on the film. Because we observe this behavior in light, we definitely see wave-like behavior, and we attribute that to an indication that light is indeed behaving as a wave. Now, what would a particle do, just to differentiate, what would a particle do if we had, say, some source of particles passing through these two slits here in our barrier? We would expect just the particles to pass directly through and go straight through, so that we would end up with two bright spots on the screen rather than just these alternating bright dark spots that we see that's due to wave. So here we see a distinction between a wave and a particle in the behavior. Waves will generate the interference effect of alternating bright and dark, whereas particles will just generate two areas where the particles hit the screen, and only in those specific two areas. All right, so what are the characteristics of a wave? Here we have an illustration that shows two different waves, and they clearly differ if we look at the crests of the waves. We'll notice that these two waves are different because the distance between the crests is different. The one on the upper part of the slide with the red, the distance between the crests is larger than on the lower part of the slide. That distance between the crests, of course, is called the wavelength. And the upper one clearly has a longer wavelength than the lower one. Right. So wavelength is a measure of distance, and therefore has units of distance. We'll frequently use nanometers when we're referring to waves because as we'll see in a moment, the region of the electromagnetic spectrum that we're going to be most concerned with experimentally is one where the wavelengths are on the order of nanometers in length. Nanometer, of course, being 10 to the minus 9 meters, 1/1000th of a meter. The other characteristic of waves, of course, is the frequency, and that would be the number of waves passing by in 1 second. We will find that frequency ranges can also be quite extensive if we look at the electromagnetic spectrum on the next slide. The units of frequency will be typically inverse seconds, or in fact hertz. Units of hertz correspond to inverse seconds. So that's what we'll be using when we talk about the properties of these waves. Now, we'll note that the wavelength and the frequency are inversely proportional to each other, and this is a relationship that shows that the product of wavelength and frequency is equal to, for the speed of propagation of any wave, and of course for light, we're talking about the speed of light, so for that would be 2.98 times 10 to the 8th meters per second. When you're doing any calculations, though, associated with the behavior of light waves, you have to be careful about units. For example, on the previous slide, we noticed that typically we'll refer to wavelength in nanometers, but if we're going to be doing this calculation and using the speed of light, you'll notice in meters per second, then we'll want to make sure that we use wavelength in meters, so you'll have to convert nanometers to meters, and of course frequency in inverse seconds. So if you take meters times inverse seconds, of course, you will get, or excuse me, meters divided by inverse seconds, you'll get meters per second unit in the speed of light. So again, the warning is just to watch your units when you're doing these calculations, particularly if you're using a calculator, which doesn't have units embedded. All right, so this illustration shows a typical electromagnetic spectrum and different types of electromagnetic radiation based on the wavelength or frequency of that radiation. Over here on the right-hand side, you have very long wavelengths on the order of hundreds or thousands or tens of thousands of meters, very long, and here's where we have radio waves, for example, in this very long wavelength region. Microwaves, of course, everybody has a microwave used to cook food these days. The typical wavelength of microwaves might be on the order of millimeters to centimeters in length. Then, of course, we have infrared radiation, is slightly shorter. And then visible. Now, visible light, that is the light that our eyes would be sensitive to, actually correspond to a very, very, very small region of the electromagnetic spectrum. In this region where we have violet light over here at about 400 nanometers and red light over here at about 700 nanometers or so, over the vastness of the electromagnetic spectrum, it's important to note that our eyes are sensitive to only a very, very small portion of that. What's significant here, of course, is that this is an evolutionary result. Our eyes are sensitive to the region of the spectrum which corresponds to the maximum output of the sun as it reaches the Earth. We see this region of the spectrum because that's the light from the sun that's used to irradiate the things that we see. So we have adapted as such. At even shorter wavelengths, of course, we have ultraviolet light, then X-rays and gamma rays correspond to the shortest. Just a quick note of frequencies here. We'll note that, for example, the frequencies can be quite large. When we're talking about visible light, for example, we're talking about frequencies on the order of 10 to the 14th cycles per second, or 10 to the 14th hertz. So this is a very, very large range of frequencies, much larger than the frequencies of say, something we might observe typically like a pendulum or something of that nature. These frequencies are very, very high. And so be aware of that if you do get a calculation. Doing a calculation associated with visible light and you get a frequency that is not a very large number, then you have probably made a mistake. So now this concludes our introduction to the properties of light. On our next video, we'll start looking at blackbody radiation and the photoelectric effect and look how these particular properties will fail when we try to explain the behavior of light classically. So stay tuned.